THHN wire is typically not an allowable method for wiring hot rail connections on a bridge crane, even with limited exposed wire. The reasons for this prohibition stem from the nature of the application and the properties of THHN insulation. Firstly, bridge cranes are industrial equipment subject to vibration, movement, and potential physical impact. Hot rail connections, in particular, are vulnerable due to their exposure. THHN insulation, while suitable for many general wiring applications within conduit, may not possess the necessary mechanical strength and abrasion resistance to withstand the rigors of a crane environment. Repeated flexing, rubbing, or accidental contact could compromise the insulation, leading to shorts, ground faults, and potentially hazardous conditions. Secondly, electrical codes such as the National Electrical Code, or NEC, provide specific guidelines for wiring methods in various applications. These guidelines are intended to ensure safety and prevent electrical hazards. While the NEC does not explicitly prohibit THHN for every possible crane wiring scenario, it emphasizes the need for durable and appropriate wiring methods based on the environment and potential risks. The NEC often requires or recommends more robust insulation types, such as XHHW or RHH, for crane applications where conductors are exposed or subject to mechanical stress. Thirdly, the fact that only 18 inches of wire are exposed does not necessarily negate the need for a more robust wiring method. Even a short exposed section is still vulnerable to damage. The risk of insulation failure is not solely dependent on the length of exposure but also on the severity of the mechanical stresses and environmental conditions. Fourthly, the term dry location does not fully address the concerns regarding the suitability of THHN. While a dry location minimizes the risk of moisture-related insulation breakdown, it does not eliminate the potential for mechanical damage. Dust, debris, temperature variations, and physical impact can still compromise THHN insulation, even in a dry environment. Fifthly, alternative wiring methods that are typically preferred for crane hot rail connections include conductors with more robust insulation such as XHHW or RHH, as mentioned earlier. These insulation types offer superior mechanical strength, abrasion resistance, and temperature ratings compared to THHN. In addition, using flexible metal conduit, or FMC, or liquid-tight flexible metal conduit, or LFMC, to enclose the conductors can provide further protection against physical damage. Sixthly, it is essential to consult the specific requirements of the local electrical code and any applicable industry standards or regulations. Local codes may have more stringent requirements than the NEC, and industry standards may provide additional guidance for crane wiring practices. Always prioritize compliance with the most restrictive requirements to ensure safety. Seventhly, it is crucial to conduct a thorough risk assessment of the specific crane installation to identify potential hazards and select appropriate wiring methods. Consider factors such as the crane's operating environment, the frequency of use, the potential for exposure to physical damage, and the consequences of electrical failure. The risk assessment should inform the selection of wiring methods and protective measures. Eighthly, the use of properly sized and installed strain relief devices is essential to prevent stress on the conductors at the point where they exit the conduit or enclosures. Strain relief devices help to absorb mechanical forces and prevent the conductors from being pulled or stretched, which could damage the insulation. Monthly, regular inspection and maintenance of the crane wiring are crucial to identify and address any signs of wear, damage, or deterioration. Inspection should include visual examination of the conductors, insulation, and connections, as well as electrical testing to verify insulation resistance and continuity. Any damaged or deteriorated wiring should be promptly repaired or replaced. Tenthly, grounding is a critical safety aspect of crane wiring. Ensure that all metal parts of the crane, including the hot rail system, are properly grounded to provide a path for fault current to flow back to the source, tripping the overcurrent protective device and preventing electrical shock hazards. 11thly, the use of appropriate overcurrent protection devices, such as fuses or circuit breakers, is essential to protect the wiring from overload and short-circuit conditions. Overcurrent protection devices should be sized and selected in accordance with the ampacity of the conductors and the requirements of the electrical code. 12thly, it's important to consider the ambient temperature in the vicinity of the hot rail connections. High ambient temperatures can reduce the ampacity of conductors and accelerate insulation degradation. If the ambient temperature exceeds the rated temperature of the THHN insulation, it may be necessary to use a higher temperature rated insulation type to provide additional cooling. 13thly, the presence of contaminants such as oil, grease, or chemicals can also degrade THHN insulation. If the hot rail connections are exposed to such contaminants, it may be necessary to use an insulation type that is resistant to these substances. 14thly, the NEC section 610.11 covering wiring methods for cranes and hoists should be carefully reviewed. This section provides specific requirements for conductor type, size, and protection, taking into account the unique electrical and mechanical demands of crane applications. 15thly, always consult with a qualified electrical engineer or licensed electrician with experience in crane wiring to ensure that the wiring methods and materials are appropriate for the specific application and comply with all applicable codes and regulations. They can provide expert guidance on selecting the right wiring methods, installing them correctly, and maintaining them properly. 16thly, while THHN is commonly used inside control panels and enclosures on cranes, the connections to the moving parts and exposed rails require a more robust solution due to movement and potential for abrasion. 17thly, consider the voltage level of the hot rail system. Higher voltage systems may require insulation with higher voltage ratings to prevent insulation breakdown and arc flash hazards. The insulation's voltage rating should be clearly marked on the wire or cable. 18thly, the type of connection used for the hot rail conductors is also important. Connection should be mechanically strong, electrically sound, and resistant to vibration. Compression connectors, properly installed and torqued, are generally preferred over twist-on wire connectors for this application. 19thly, if the crane is located in a corrosive environment, such as near a chemical plant or saltwater, it may be necessary to use corrosion-resistant conductors and connectors. Copper conductors with a tin coating or conductors made of corrosion-resistant alloys may be appropriate. 20thly, be aware of the potential for induced voltages in the hot rail conductors. Long runs of parallel conductors can induce voltages in each other, which can create electrical noise and potentially interfere with the operation of the crane's control system. Shielded conductors or twisted pair conductors may be necessary to minimize induced voltages. 21stly, consider the impact of electromagnetic interference, or EMI, on the crane's electrical system. Cranes often operate in environments with high levels of EMI, which can disrupt the operation of sensitive electronic equipment. Shielded conductors, filters, and grounding techniques may be necessary to mitigate EMI. 22ndly, the color coding of the hot rail conductor should comply with applicable electrical codes and standards. Proper color coding helps to identify the conductors and prevent wiring errors. Typically, black, red, and blue are used for the ungrounded conductors in a three-phase system, while white is used for the neutral conductor and green is used for the grounding conductor. 23rdly, ensure that all wiring work is performed by qualified personnel who are trained in crane wiring practices and safety procedures. Incorrect wiring can create serious electrical hazards and damage the crane's equipment. 24thly, maintain accurate documentation of the crane's wiring system, including wiring diagrams, cable schedules, and test reports. This documentation will be helpful for troubleshooting and maintenance purposes. 25thly, consider using cable trays or cable carriers to support and protect the hot rail conductors. Cable trays and carriers provide a neat and organized way to route the conductors and prevent them from sagging or becoming tangled. 26thly, the use of surge protection devices, or SPDs, can help to protect the crane's electrical system from voltage surges caused by lightning strikes or other electrical disturbances. SPD should be installed at the main power entrance to the crane and at sensitive electronic equipment. 27thly, be aware of the potential for static electricity buildup on the crane's structure. Static electricity can discharge through the electrical system, causing damage to sensitive components. Grounding the crane's structure and using static dissipative materials can help to prevent static electricity buildup. 28thly, the selection of the appropriate wiring method for crane hot rail connections depends on a variety of factors, including the operating environment, the voltage level, the potential for mechanical damage, and the applicable electrical codes and standards. It is essential to carefully consider all of these factors and to consult with qualified professionals to ensure that the wiring system is safe, reliable, and compliant. Remember to always prioritize safety and adhere to the relevant electrical codes and regulations when working with crane wiring. Improper wiring can create serious electrical hazards and endanger lives.